morning class and welcome to another lecture in sustainable energy technology. Today we will continue our discussion on biomass and bioenergy based sources, and we will look into a little bit more detail on various types of important biomass and bioenergy based fuels, how they are produced and how they are utilized for different cases. The first important biofuel type that we will discuss today is biogas. As we discussed in the last class, biogas is a gaseous biofuel which is obtained from the anaerobic digestion of wet biomass. This is a very important aspect because many types of biofuels require pre-drying, whereas biogas can be directly produced from wet biomass. In fact, it needs moisture for its processing. So there are many types of biofuels which have a large moisture content, like municipal waste, agro waste, then organic waste from cattle farms, animal farms, etc. And these can be directly processed to produce biogas without any significant effort or energy needed to pre-dry them. The primary process by which biogas production happens is anaerobic digestion. Anaerobic digestion occurs between 30 degrees centigrade and 50 degrees centigrade in absence of oxygen, with higher temperatures leading to better conversion efficiencies. So if we go towards the 50 degree centigrade side, then you will get better conversion efficiencies for biomass to biogas production. And when we are saying anaerobic digestion, it basically means there are certain types of anaerobic microorganisms which help reduce the biomass and produce biogas, and all of this happens in absence of oxygen. So what this means is we need an area where there is no oxygen for this kind of digestion process to occur. The process is typically slow. The typical residence time of biomass in an anaerobic digester is around 2 weeks. So because it's an organic process, the conversion is quite slow. So you typically need very large digester systems to process large volumes of this biomass to produce biogas. Okay. So this is a schematic of how this system works. We have liquid biomass which is being fed into your system, and certain additives are added to this liquid biomass to enhance the processing to biogas. Then this additive enhanced liquid biomass is entering your heated anaerobic digester, which is either insulated or heated to around 40-50 degrees centigrade to enhance this conversion process. Here we have the microorganisms, certain types of anaerobic bacteria which basically uses this biomass source as food, and basically the biogas is a byproduct of this bacterial processing. So this biogas accumulates at the top and is then separately flowed out into biogas containers. At the bottom, a certain solid sludge is produced which is taken out periodically, and this is called solid biodunk. So basically the liquid part of it gets converted into gas and part of it gets converted into a solid byproduct which is called solid biodunk. Okay. Now the content of biogas, the primary content and the content that has the energy value of biogas is methane, and depending on the type of waste that is used and the process that is being followed here, the content of methane is around 50% to 75% by volume. The next most important component of biogas is carbon dioxide, which is around 25% to 45% by volume. And then you have a little bit of water vapor, clearly there will be some water because it's a liquid system that you were putting in, so the water remains. So around 2% to 7% is water vapor, and there is a small amount of hydrogen sulfide, less than 1%, which is present also as a byproduct. So typically these biogas processing facilities will have the smell of rotten eggs, which is familiar smell of rotten eggs because of this process. But in the biogas, the most important component is methane, which gives it its energy content. Okay. So what is this biogas used for? As the primary content is methane, this biogas can be blended with fossil based methane and used directly for heating systems in industrial furnaces for process heating applications. So it is a natural replacement of fossil fuel based methane. Now the yield of methane in terms of volume per ton of biomass depends on the feedstock that is being used. Okay. So this is the biomass feedstock that is being used. It's like maize silage, basically the waste from a maize cultivation plant. Grass silage, basically grass fodder kind of system. Cattle manure, so manure that is from animal farms. Then liquid manure, this can be municipal liquid manure, for example. So these types of sources can be used for biogas production. Here is the yield of biogas in terms of meter cube of biogas produced per ton of biomass source. So for maize silage, for example, 200 meter cube of biogas is produced per ton of maize silage on average. This, if you go for grass silage, is around 170 meter cube per ton. The values are significantly lower for cattle manure and liquid manure, which are far more wet in their, it has far more water vapor, for example, and so the yield is lower, around 45 meter cube per ton and 20 to 30 meter cube per ton for liquid manure coming from municipal sources. The methane percentage also varies between the various sources. So for example, for maize and grass silage, it's around 54 to 53% methane at the lower end, whereas for cattle manure and liquid manure, the methane content is higher, around 60 to 65%. So both the yield and the methane percentages are different based on the different biomass sources that are being used. Biogas can be mixed with natural gas, as we discussed, and can be used in furnaces to generate heat or in power plants to produce electricity. So those are the two main ways in which biogas you can use it. You can produce heat in furnaces, or you can mix it with natural gas and produce electricity as well. And the main digestion process for the various feedstocks is described here. So this is carbohydrate C6H12O6. So this is the primary constituent in, for example, vegetable matter. So maize silage, grass silage, these will primarily made of carbohydrates. So when it breaks down anaerobically by the bacteria, it produces 3 moles of CO2 and 3 moles of methane. So that is why for maize silage and grass silage, you will get around 50% methane by volume, and the rest will be CO2. For animal waste like cattle manure and liquid manure, the primary content is more fat and protein, which have a different CHO ratio. So for fat is C51H98O6, for protein it's C13H25O7, and these will also contain significant amount of water. So the water is also included here, and this will produce around 14.7 moles of CO2 and 36.25 moles of methane. So this is more or less 1:2 ratio of CO2 to methane. So you get methane up to 70% in these cases. Similarly, for if it's protein, then it's 5 moles of CO2 and 7.8 moles of methane. So here also methane content is higher than CO2, but not as high as fat. So animal waste will contain a mixture of fat and protein. So the methane percentage will vary depending on how much fat and how much protein is present for the two cases. Okay. Now the advantages for the two cases are as follows. So one advantage of biogas production is as follows. There is no need to dry wet biomass. It can process wet waste quite easily. So municipal waste, livestock waste can be easily be used to produce biogas. Also the exit solid biodung stream. So if you remember, we had the solid biodung here. That exiting solid biodung stream is environmentally benign and can be used as fertilizer. So you can use that biodung as an environmentally benign fertilizer for organic farming purposes, for example. So both the products, biogas can be used for heating and electricity applications, and biodung for agricultural fertilizer applications, are economically attractive propositions. So the location of these types of biogas production units are like large breweries, crop industrial farms, so industrial croplands, urban sewage plants, cattle and pig farms, etc. So it produces it gives the twin purpose of processing waste that could have been toxic to the environment and producing both energy and high value fertilizer out of it. Now we will look at a little bit more detail of how do you design a biomass to biogas conversion digester based on the amount of power you need and the amount of biomass feedstock that is available to you on a per day basis. Okay. So the energy available from a biogas digester is given by this expression. So let's look at this expression little by little. So eta is the efficiency of combustion of biogas in a furnace. So we are assuming here that the biomass source, the biogas will be used in a furnace for heating purposes. So the combustion efficiency of biogas in a furnace is around 0.6. So 60% of the heat produced by burning the biogas is actually used in heating. So that's the efficiency of combustion. Then HCH4 is the heating value of methane. That is how much energy is being released when you burn 1 kg or 1 meter cube of methane. So the heating value of methane is around 56 megajoules per kg or 28 megajoules per meter cube at STP. Okay. So when you are looking at per kg, it's fine. If you do it per mole, per volume basis, then since the volume is changing with pressure, we usually give the volume at standard temperature and pressure, which is 300 kelvins and 1 atmosphere pressure. So the heating value of methane is 56 megajoules if you burn 1 kg of methane, or 28 megajoules if you burn 1 meter cube of methane at standard temperature and pressure. Then FCH4 is the fraction of methane in biogas, which is around 0.5 to 0.6. So this basically varies between one type of feedstock to another type of feedstock, as we discussed. Because biogas contains 50 to 60% methane, this FCH4 basically varies from 0.5 to 0.6. Okay. Finally, the V gas is given as meter cube of biogas sent to your furnace per day. Okay. So how much volume of biogas you are sending to your furnace on a daily basis. So this is given by C into M0. C is the biogas yield per kg of dry biomass. So how much yield of biogas is happening per kg of dried biomass. This was given by the table before. So this is meter cube of biomass per kg of meter cube of biogas per kg of biomass sent to your digester at standard temperature and pressure. So this is your C, and M0 is the dry basis mass input of your biomass source to your digester per day. So suppose you are sending 100 kgs of biomass, say for example cattle manure, to your digester on a dry basis per day. So your M0 is 100 kg. And the yield is say 20 kgs of biogas is produced per 100 kg of cattle manure entering your digester. So yield will be let's not 20 kgs, 20 meter cube. So the yield is 20 meter cube per 100 kgs. So then this C into M0 will be 20 meter cube. Okay, so this gives you the volume of biogas that is being produced from your digester on a per day basis. Okay. So these three gives you the total energy available from a biogas digester. Okay. Now the volume flow of fluid, now this is the dry basis biomass that you are sending, but the biomass you are actually sending is a liquid sludge. Okay. So the fluid that you want to flow into your digester is given by Vf as meter cube of fluid flowing into your digester per day, and this is given by M0 by rho m. Remember, M0 is the dry basis biomass mass input and rho m is the density of dry matter in the fluid entering the digester. Okay. So your digester will be a liquid sludge. So here the idea is how many kg of dry biomass is there per meter cube of the liquid sludge that is entering your digester. So typical values are around 50 kg per meter cube. Okay. So suppose 100 kgs of dry biomass is entering the digester and your liquid sludge solid density is 50 kg per meter cube. Okay. So that means 100 by 50, 2 meter cube of liquid sludge is entering your digester on a daily basis, and that is your Vf. So then the volume of the digester that you need is the volume of fluid entering per day and the residence time of that fluid in the digester, which is typically 8 to 20 days. So if 2 meter cube is entering per day and your residence time is 20, then the total volume of your digester needed is 2 into 20 or 40 meter cube. So that gives you the minimum volume that is required in your digester to fully process the flow rate of the biomass sludge that is entering your system. Okay. So that gives you a basic idea of how to design your digester. The next biofuel type that we will discuss is bioethanol. So as we discussed earlier, bioethanol is a basically ethanol produced from say sugarcane or primarily sugarcane, but you can also have corn based ethanol, and this is used as a replacement of petrol in cars. Now ethanol, the primary way by which ethanol is produced is through alcoholic fermentation. Okay. So ethanol, which is ethyl alcohol C2H5OH, is produced naturally by yeast. The yeast is basically a microorganism whose scientific name is Saccharomyces cerevisiae, and this yeast basically produces ethanol from sugars at acidic conditions where the pH values are around 4 to 5. So this process is very much common in wineries and distilleries where the yeast is used to break down sugar and produce ethanol under acidic conditions. The ethanol concentration produced by yeast is around 10%. Okay. Now so the rest is basically water. Then you basically do a fractional distillation where because ethanol and water has different boiling points, you boil it and the ethanol boils earlier, you then condense ethanol separately and do this several times to reduce the proportion of water. Okay. So this fractioning and distillation process creates finally a 95% ethanol and 5% water mixture. Now this mixture is called an azeotropic mixture because it has a constant boiling point. So distillation based separation will no longer work after this point of time. So what we want to do after this point is we use solvents such as benzene to produce anhydrous ethanol. Okay. So after you get to a position where you are getting 95% ethanol and 5% water, you use benzene which absorbs the rest of the water to produce anhydrous or 100% ethanol. And this ethanol can be used in blended form in petrol for car engines, scooters, autos, etc. Now the primary process in which yeast converts sugars to ethanol is listed here. So sugar is primarily, for example, sucrose, which is C12H22O11, the primary sugar that is present in sugar cane or molasses. This, along with water and in the presence of yeast, breaks down into 4 moles of ethanol and 4 moles of CO2. And this ethanol is being used primarily. The other process by which ethanol can be produced is breaking down sugar from starchy crops like barley, corn, cassava, etc. Now starch is somewhat different from typical sugarcane based sugars because it's basically long chain carbohydrates linked with glucose molecules which are dangling from the carbohydrate chain as branches, and enzymes from malts. Malts are again a certain kind of bacteria from barley and corn malts or from molds like a fungi based molds can be used to break the starch and release the glucose. Okay. So glucose sugar to ethanol conversion requires molds and malts, and this is usually common in like beer making distilleries, etc., which typically use this process to produce ethanol from wheat, barley, corn, etc. So the third type of ethanol production, and this is under more of a research stage, is ethanol from cellulose. So cellulose is basically this is the second generation biofuel production technique. Cellulose is basically the material that is present in basically leaves of plants or the bark of plants, which is lignin. So lignin and cellulose together, and these have polymeric structure of linked glucose molecules, and these links are usually very stable and much harder to break down. Okay, so hydrolysis using enzymes of naturally occurring wood rotting fungi, you can break this down and produce ethanol, but the process is very slow. So the current research is focused on speeding up the enzymatic cellulose to ethanol conversion process. Okay. So cellulose is a polymeric structure, and breaking down cellulose and releasing the sugars for conversion into ethanol is usually very challenging, and it is a very slow process naturally. So there is a lot of research going on to create better enzymes, and some success has happened, but the costs are still too high for full scale commercial production. But this is a very potentially extremely attractive source because cellulose and lignin are far more sustainable sources for ethanol production than sugars from food crops or sugarcane based systems. So hence there is a lot of research starts to create cellulosic ethanol which is in a commercial scale. Okay. Finally, the final type of biofuel that we will discuss is biodiesel from vegetable oil. So concentrated vegetable oil has poor combustion characteristics and needs to be processed to be used in diesel engines as diesel substitutes. So here by vegetable oil we mean sunflower oil, rapeseed oil. If you are looking at non-edible vegetable oils, it can be jatropha oil. So any type of oil that comes from vegetables, groundnut oil, etc. Now vegetable oils cannot be directly used because these are basically organic acids, and they have poor combustion characteristics and can be corrosive to the engine. So instead what we do is what is called a trans-esterification process, where these organic acids in presence of methanol is converted into methyl esters. Okay, and these methyl esters are far less corrosive and has far better combustion characteristics, making them ideal substituents of fossil diesel in trucks and diesel based cars cars. Okay. So we react vegetable oil with methanol or ethanol to form methyl or ethyl esters. These are called fatty acid methyl esters. The fatty acid chain is the large aliphatic chain that is on this side. This has 18 to 19 carbon molecules. So CH3, CH2, 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 CH2 like that, 18 to 19 of them. Then you have the ester bond, methyl ester bond, C double bond O CH3. So that is why it's called the fatty acid methyl ester or FAME biodiesel. And the process is called transesterification and requires potassium hydroxide as catalyst and produces glycerol as byproduct. Okay. So that's how biodiesel is produced. So in today's class we covered 3 basic types of biofuels that are widely used and their processing technologies and how they are actually produced by different methods. So this kind of completes our discussion of biofuel and bioenergy sources. In the next class, we will start our discussion on geothermal energy as a resource. Thank you for watching and see you in the next class.